In the AI space today, there's a lot of hype about what these tools can do. Like, we've been led to believe that AI can just wave the magic wand and solve all the problems with businesses. But that's not really the truth, and the data shows differently. And as a researcher, my main question is always to ask why. Why is this happening? So after talking to hundreds of people in the space from all different backgrounds and ICPs and personas, what I've really come to learn is that most people don't really understand how LLMs work. And when they don't conceptually understand the base foundation of how these things operate, it's really easy to be led astray. And a lot of the marketing from some of the biggest firms out there lead everyone to believe that if you just give all of these things data, that they will become intelligent and will be this magic wand to solve all the problems. And that's not quite the case. So today we're going to quickly talk about really how these models work. And the key thing to walk away with is that, context is not intelligence and there is a difference. However, we can create intelligence using these models. So we'll go ahead and get into it. So today we'll be talking about how do you use prediction machines or large language models to actually build levels of intelligence. Now, as we said before, this technology is really kind of offering and promising a ton of different stuff to businesses, but 3 out of every 4 companies is failing at AI. Now, again, this isn't the company's fault, and I don't blame any of them. I think a lot of the blame comes to, the marketing and maybe some of the false reporting of metrics, but it's really leading to this idea that these models are intelligence when they're not. Because we were promised and we were told that if you just give AI, we give you our model, or if we give you our tool and you just give us your data, we'll be able to wave the magic wand and you'll have all of these infinite productivity gains. You might even be able to replace some of your workforce. And this just isn't true. And companies and the industry as a whole is failing to mitigate that. In my firm understanding, in my background, and what we want to look at, and it begs the question of why. Like, if this technology is so revolutionary and is so good, like, why is it failing? Like, what is going on that's leading this to happen? And after talking to hundreds of different customers, hundreds of different people in the space, what I've seen as a common thread in all of this is that there is this misunderstanding that context is intelligence, meaning that if you just give this data, if you give these models more data, you give it more context, it will be intelligent. It will be able to answer these questions and these things that you're thinking about. But what the data is showing is that that's not true. Like, we have seen and seen over again that this notion of just giving models more and more data will lead it to this, promised land of being able to be the magic wand and be able to solve all these problems. But there's tons of data out there showing that if we just give it more information and more compute, these things are starting to plateau. It's a big problem in the space that if you've seen the recent models coming out from OpenAI and Claude, they are not exponentially better than the ones before. They're getting incrementally better. So we had the hype up and now they're kind of doing this. But we're leading a lot of the market to believe that if we just give it more data, it'll solve it, but that's not the answer. As we said before, context is not intelligence. But what we do want to walk away from this video is that you understand how large language models work. Well, this video is not about selling product. This is about educating on what these models do and how they work so you can better set your own expectations on what to do, as well as how you might be able to use these prediction machines to build intelligence. So LLM at their core, as I said, they're just prediction machines. Their job as a problem statement is to predictably and reliably and statistically guess what the next word in this sentence will be. And as data moves through, something like ChatGPT as an instance, you pass in the word the, maybe the next probable word is cat, and then after cat it's likes, and then to and sleep, in something, and so on. And it does this just over and over and over, and that's how it forms natural language in ways that we can do it, or the ways that we can read it and understand it. And it seems magical. It seems so easy to anthropomorphize these things. But really, it's just pattern matching. But a lot of this gets misconstrued into that it's super complex and there's hard math and things going on, but no one really knows what it looks like. LLMs are black boxes, and they are to some level of degree, but we can kind of crack them open. And if we use an open model that we can test, such as GPT-2, it looks kind of like this. So within a large language model, they have these things called graphs. And so at the top of this is you can see a graph, which is basically a dot or a node with some direction to others. Now in these, it's weights and probabilities that how probable is this other dot to follow this one in a sentence. And if we project this down into 2D space on the second row here, you can start to see these map out. And then we can further project this into 3D space. Now doing this on a very small graph looks similar here, but we can do it with a lot more nodes and a much bigger graph, and you kind of can look at a small slice of the brain of GPT 2.0 as it's thinking through a problem. And what we're really looking for in each of these are called attraction basins. So you can imagine that this topography starts off flat. When we get the previous word coming in, it all of a sudden starts to morph and form and say, okay, based on this, this is probably the next word. And with some pretty simple calculus, you can find these attraction basins really quickly. So again, just to reinforce that all these models are doing are running through a probability machine at a nth degree to be able to come up with this stuff. But if we take our previous example, talking about the cat likes to sleep in, GPT processing this, taking a kind of snapshot of the different layers, because again, it just kind of feeds all the way through multiple of these layers. It looks kind of like this. So this is the best representation we can do of how a large language model looks when it's thinking. Like this is what's kind of the inside of the brain of this model. And if we want to even project this into somewhat 3D space of moving through all of the different layers, you can think those ones before, just a few slices here. You can see this moving through vector space, and this at the far right is kind of how it pops out whatever the next word is. And then it just feeds through again, and feeds through again, and feeds through again. Now, the market would believe, and a lot of companies tend to believe, that if we just give it more data, maybe if we just expand the context window of these machines, they will get smarter. So that's kind of the first port of call. Base model isn't working. Let's expand the context. Let's expand how much data it has access to or can think about at any one point in time, and maybe it will become intelligence. But that's not the case. So this, if we want to take context windows for perspective, that at the time of writing, GPT-4o is about 128,000 tokens, 128,000 little things it can keep in its memory at any point in time when it's trying to predict what that next word will be. And that seems like a lot, and it probably works pretty well for some basic things. But if we're talking about using this for code, more specifically for modernization of code, where you're dealing with large code bases, 1 million lines of COBOL is about 12.5 million tokens. That's just for 1 million lines. A lot of these legacy code bases are 8 million, 10 million lines. So to think that we're going to solve this problem by just taking 128,000 tokens when we need 12.5 million, we've got a gap. But Cory, maybe the answer is just expand the context window. Why can't we just make it bigger to fit 12.5 million tokens and then problem solved? Well, this is when we come into a paradox. And this is kind of generally referred to as the needle in the haystack paradox, where basically if you start to give these models too much context, they kind of forget what's important and they kind of start to hallucinate and they go off the rails, which if any of you have chatted with Claude or ChatGPT for a long period of time, you notice once you really get deep down in there and kind of past or up to the upper limits of what a context window it has, it can start to really go off the rails. Now, the next protocol for the industry was to go to RAG, or Retrieval Augmented Generation. And this, again, is not solving the problem. All RAG is doing is making sure that it's pulling relevant data that it can put into the context window when you're asking it a question. So it's just kind of shuffling papers quickly to the model to say, here, think about this, or here, think about that. But again, it's not driving intelligence. It's not really driving it beyond pattern matching. It's just giving it, different patterns to match against. Okay, so if that's not quite getting us where we need to go, the next option is fine tuning. Now, this is probably the best option you can do, but this is incredibly expensive. This is when you're taking a core base model and adding additional data on top of it. But while you might be fine-tuning the model, and it is a really good option, it's a very expensive, very tough option, it's still not building it beyond just a prediction machine. You're just giving it better, baking in better data for it to predict upon, but we're still stuck in context and we haven't quite figured out the intelligence side. Because again, context is not intelligence. There is a difference here. So then the question becomes can we create intelligence using prediction machines? Well, it turns out actually we can, because LLMs alone are not enough. If all we just have is a prediction machine, it doesn't have intelligence. So how do we build something that you can pair these together with to actually get us all of these promises that have been made? And as we talk about intelligence, the way that we define it is that intelligence is structured knowledge. It's understanding things like relationships, so it can go and understand beyond basic decision making and beyond just pattern matching. Like we really truly want reasoning in these things. Now, the way that the models out there, and some tote, that these are reasoning machines, large reasoning models, is that they're basically just asking themselves questions back and forth, but their still underlying architecture is just pattern matching. So while you might get some gains in being able to think through a problem by challenging itself over and over, its base architecture of pattern matching has not changed. And so using kind of intelligence in this way, in the way that we do it, we create intelligence models, not LLMs, but intelligence models, meaning that as you're using a large language model or it's being leveraged, it doesn't have to figure out these rules. It doesn't have to do this type of complex reasoning on its own. This intelligence is already encoded into an intelligence model that makes responses from the LLM more consistent, predictable, and aligned with business intent. Now, again, when we talk about intelligence models, we don't mean fine-tuning, we don't mean RAG, we don't mean expanding context. We mean building a net new asset that sits next to these models that has deep levels of understanding beyond just pattern matching capabilities. And so if we look at how we do this, I think the interesting part that we've taken and we've started seeing, and this is very contradictory to, I think, how a lot of things are going in the space, is that the best way to use AI is to use as little AI as possible. AI is non-deterministic, meaning that every time you ask it a question, it may give a different answer. So in the enterprise context, this is a problem. So the way we go about creating intelligence models is actually leveraging LLMs as a piece of the puzzle, not the whole puzzle itself. So using things like inference-based analysis, static data analysis, challenging a gap back against the original data, strong evals, and human feedback, we put all of this together to generate what we call this intelligence model. And the way that an intelligence model is leveraged or is used is in tandem with two other very core assets, one being LLMs, and then the third being the well of data, your truth, or as Google calls it, your force. And by using all of these three together with an orchestrator layer in between, we actually become very thoughtful about how answers are retrieved and given back to users or applications, meaning that if we don't need to use an LLM and we can just get the raw information from the well of data itself, you should always go to the deterministic solution. Now, that doesn't always work. And sometimes you might need to leverage an AI to do something. But what we've seen is that using an intelligence model in tandem and next to an LLM drastically produces the performance. And we care about this a lot. Like, we really care about how do we improve what these core models and these great companies are out there producing. So much that we even spent a ton of time to run a full empirical study with GitHub and Microsoft to understand what would be the impact of having this intelligence model sit next to a code gen. So we tested basically how would providing business context and intelligence to code suggestion and code generation of GitHub Copilot work, and how much would it actually improve its functionality. Well, it actually had a 51% relative increase in its code suggestion acceptance rates, and that's huge. That means that the code that is being suggested to developers in real time, in line, started to be accepted much more frequently, because again, this LLM that's generating the code suggestions now has intelligence about what the business and what the project and what the goals are trying to do. It doesn't have to reason on its own. We've already done that. We've already encoded all of that information for it. And so an intelligence model at the end of the day is basically defined by 5 different things. So it's pre-computed knowledge graphs that capture things like business rules, system relationships. It's encoding reasoning patterns to understand why and not just what. Now, this one is really important because a lot of times, if you're trying to use large language models to do something with big code bases, you know what it does. You know what the code does because you can go look at the application. That is the what. And sometimes large language models would be good at telling you how it does it. Maybe it's, being able to track code or code calls, but what it can't do is tell you why. Why is this stuff working this way? What is the intent behind some of these things? So encoding that is really, really important. Structured relationships, business intent, so being able to take in things besides just data sets, but mapping it back to business intent, as well as persistent and queryable. One of the big things that we pride ourselves is that can we get consistent outputs that leverage intelligence models and large language models so that user experiences are consistent, you can benchmark, you can test a lot better, and you get all of this through this intelligence model that again sits adjacent to large language models. And this is more important than ever. We've seen a ton of interest and a ton of capabilities and applications of intelligence models when doing legacy code modernization, but the industry and the world is in a very interesting, kind of predicament in that from behind us, we've got this crushing need to modernize. This one's here, there's 8 billion lines of COBOL out there still running our world, our financial system, planes, scheduling, crew scheduling systems that's still out there running the world that needs to be modernized. But now there's a new kind of, sheriff on the block, and that's AI code gen. These models are, developers are using these, or click a button, get an app, and there's 50,000 lines of code that's undocumented that have no idea what it does. So being able to apply this intelligence not only to legacy code, but also this market and this problem that's growing right in front of us is paramount. And it's so important for enterprises to understand that this is an existential risk coming to there, but we won't get into that today. Because just in kind of the last, I believe this is like 12 months alone, there's been 256 billion with a B lines of code generated by AI. And our capacity to understand code is way behind our ability to produce it. We are producing at a much faster rate than we can ever hope to understand, and this is a problem. So one of the most recent results or recent reports, the main ones to look at here are the green and the red lines. So the green lines is the amount of code added going into GitHub, obviously going up as it should, sharply going up with the advent of AI, but the red one is the scary one. The red line is the scary line. This is churn. This is the amount of code that was added and had to be removed or rolled back because it didn't work. And odds are the big driver of all of this is that we've got AI out there just spitting stuff out. No one takes the time to understand it. They click commit, it goes into the repo, all kinds of problems unfurl. So having intelligence models that can help prevent this and help secure you against this is now more important than ever, even if you are facing legacy code and modernization issues. But luckily, we've been thinking about this a lot. I said I wasn't going to do a plug, but we have to do, because we've been thinking about intelligence models and this problem in the space for a very long time. And so when we think about code intelligence, our intelligence model is basically sliced up into 3 different layers. Layer 1 is really code intelligence. So how do you deeply understand, like at the code grain itself? How do you abstract that intelligence out 1 layer into things like architecture, and then abstract it out again into things like business intelligence, things like business logic, business rules, business intents, and how do you make this accessible to everyone? And we've seen this intelligence model, again, coupled with generative AI to do a lot of really cool things like legacy modernization. You've got a giant COBOL database or COBOL code base. You're trying to understand the forest for the trees, and it's impossible to do so. Things like application maintenance. So again, this is an example from a COBOL thing, that COBOL application. They had no idea how the batch workflows ran. Everything was kind of all over the place. So being able to deeply jump in and understand that. Improving code generation, as we showed with the GitHub research study, and a number of other ones. And all of our system and intelligence models are completely accessible via API, so that you can do things like integrate it into your existing workflows to really get the most out of this. And where we see the market going, that the need for this intelligence is going to be exponentially higher. One, because the models themselves are starting to hit the top line, and fundamentally because these models are just built on the same architecture. They're not getting the same jump per model version as we saw before. And the other kind of big reason, as we mentioned, is that we're in a very interesting spot in history when it comes to code because of AI code gen. So when we see a situation where kind of the core tech is topping out, restricted by its fundamental infrastructure, as well as this kind of existential crisis of a new risk coming in, intelligence models as a pair or as a sidecar to what these models are, existing LLMs are able to do is so powerful. So if you want to learn more, if you found this interesting, please let us know and please reach out.